All right, so welcome to Math 331. This is lecture 8. And what I want to do today is I want to talk a little bit more about methods of proof. And so I'm going to start with a problem that should be extremely familiar to everyone, the Pythagorean theorem, talk about how to prove it, talk about advantages and disadvantages of different approaches, and then talk about how to extend it. So I can't remember if I shared with you all that one of my former students sent me that Google now has a feature where you can feed a paper into Google and it will generate a podcast where people discuss your paper. It's incredible. So the host really sounds like a host. It's much easier to ask questions than to answer questions. And the host is asking really good questions, good choice of tone and whatnot. The respondent is not quite there yet. It's okay, but you can definitely tell at times that the respondent is just lifting sentences from the paper that they don't really understand. Give it a few more years though, and it will be there. But there's a bunch of generic questions you can ask whenever you see a math problem or just a problem in life about what can you do next. And that's one of the things I want to teach you this semester so that when you see possibilities, you have a good idea of what to do next. This is not June 30th, 2015. I'm just too lazy to change the date on the slides. Okay. So what I want to do is talk about some key phrases. So I was a postdoc at a school whose mascot is the Buckeyes. Anybody know what school that is? The full name of the school, please. The Ohio State University. It's not a Ohio State University. It is the Ohio State University. In mathematics, we normally don't say the. We don't say the proof of, we say a proof. Now, for some things, we actually talk about the proof. So Erdős talks about how you do not have to believe in God, but you have to believe in the book. And the book is where God has written or somebody has written all the best proofs of results. And sometimes there are multiple entries for the same theorem. Just brilliant, elegant arguments. I have a copy of a human approximation of the book in my office if anybody ever wants to borrow it. If you're looking for colloquium talks, wonderful source of things to look at. Different proofs will often highlight different aspects of the problems, and they'll often generalize to other things. So the more proofs you see of things, sometimes the better. And so we're going to start today by doing the Pythagorean theorem. If you do not know the Pythagorean theorem, this is where you have to just be able to go, oh yeah, and like scratch it and you wave your hand and pretend that you know what it is. This is something that everybody should have seen by now. And it would just be too painful for me to see people not knowing that. If that happens, quickly learn it later. I won't ask, but the first time I taught an advanced seminar at Williams, I was shocked when I learned that 7 out of 21 students had not seen e to the I theta in a senior seminar. So I understand that there are some things you would like students to have seen, but they have not seen. Pythagorean theorem, you must have seen. That doesn't mean that if you are put on the spot that you could give a proof of it. Hopefully you can. Something that is so important as the Pythagorean theorem. One of the most important applications of this is we use it to measure distances. How far apart are two objects in Euclidean space? So if I give you a right triangle, we always label the sides A and B. You have some freedom as to which way do you want the triangle to be drawn. Do you want A to be the vertical or the horizontal? So you have a little freedom, but not much. A squared plus B squared equals C squared. And it's a nice exercise to ask which triples of integers A, B, and C can you have satisfying this relation? And there are nice explicit formulas that will tell you all the A's and B's and C's that will work. Out of curiosity, how many of you could prove this right now if your life depended on it? Not seeing that many hands going up confidently. If your life depended on it.
If you ask me to right now, probably
not. Right. All right, so let's do. So this is the famous proof going back to Euclid, Book 1, Proposition 47. And you can see, like most good geometry proofs, there's lots of auxiliary lines. Some are solid, some are dotted. All right. This is basically the same, except now we're using color. And sometimes putting in color does make things a little bit easier to see. I strongly urge you to go through and try to make sense of these proofs. As always, the slides will be posted. Can you go through and understand why these are true? What it's clearly showing here is the two oranges must be the same, and I'll call those the two reds must be the same. That's very different than the previous one where it's not quite clear how I'm showing everything is the same. Yeah, what is a squared? A squared is the area of a square with side length a. And that's why I'm drawing these squares coming off the triangle. And so by putting in the colors, it's basically telling you I'm splitting the long hypotenuse c squared into two rectangles. And the orange rectangle on the bottom is equal to the square, and same thing for the red. Here's a beautiful proof. All right. Notice the different colored regions have numbers. I've never really tried to figure this out, but what do you think must be true about the two regions labeled 1? Yeah, they better be the same, right? And so somehow someone found this way of carving things up. Okay, so nice exercise, make this rigorous. This is the first proof I remember. I was a freshman at Yale, and my physics professor showed us this. So imagine you have a square of side length a plus b. So then the area of the square is going to be the quantity a plus b squared. And we can take the right triangle with sides a and b and take 4 of them and put 1 at each corner as shown here. And with a little bit of work, you can show that the region inside has to be a square. So for instance, if the angle, the small angle next to A is theta, the angle next to B is 90 minus theta, then the angle over here would have to be, let's see if I can actually write this. Can I write this? Let's see. Nope. Then this would have to be 90 minus theta over here. Since it has to be 180 because it's a horizontal line, that gives you a right angle over there. So this has to be a square inside. And now what you do is you use the fact that we know the area of a rectangle and we know the area of a right triangle. So whenever you're proving something, the question is always, what are you allowed to assume? We will assume as our basic fundamental building block that we know the area of a rectangle is length times width. That seems like a reasonable, fair game to start with. If I split a rectangle diagonally, that gives me 2 right triangles. And since the 2 of them are similar and the area should not be changed under just a rotation, again, this is another assumption from geometry, then the area of a right triangle should be what relative to the area of the rectangle it lives in? So what should the relationship of a right triangle be relative to the area of the rectangle that it lives in? Half. And that's how you get the area of a rectangle is xy. The area of the right triangle formed by cutting it diagonally is 1/2 xy. So I'm just using these basic results. And so I calculate the area of the big square 2 different ways. And this is a key proof technique. Calculate something 2 different ways. If you're calculating the same quantity, they must be the same. So you get quantity a plus b squared is going to be the same as the 4 triangles. So 4 times 1/2 ab is 2ab, and the little square, which is c squared. So when you expand, you get a squared plus 2ab plus b squared is c squared plus 2ab. We subtract 2ab from both sides, and there's Pythagoras. A squared plus b squared equals c squared. So that's, I think, the simplest proof I know of. You had to be clever in how you put things together, but it's not too bad. Here is a slight modification of that proof. Again, similar to some of the other ones of just showing that I can match things up and seeing the a squareds, the b squareds, and the c squareds. So I'll leave this to you to fill in the details. Who is the best president in US history if you are a Williams undergraduate? Garfield, right? Why?
I live in Garfield House.
You live in Garfield House. Yeah. It's interesting that you don't say anything that he did as president just because I went to Williams and I live in Garfield House. All right. So as a professor at Williams teaching a math class discussing the Pythagorean theorem, it's very hard to lose your job if you're tenured. Not mentioning Garfield right now might be enough to do it. So we have to honor Garfield because he's credited with a proof of the Pythagorean theorem. And his proof is completely different than this proof we're seeing over here with a square inside a square. this trapezoid, which might look like part of that square, it's completely different and absolutely deserves to be isolated as a valuable contribution to mathematics, right? So I'll let you go through the argument that he has of the trapezoid, that this is going to give you another proof of Pythagoras. And you might need to know some facts about the area of a trapezoid. And again, it's always, what do I need to prove that? Again, trapezoids we can always get from rectangles and right triangles, so it's not too big of a deal. All right, so we're going to see, or we've seen that there's lots of different proofs. The hardest part in all these is, how did people come up with these combinations? How did they come up with drawing these auxiliary lines, splitting things up the way they did? How do they show that the different matchings all add up together? There are lots of different proofs. A lot of the proofs you can follow line by line. At the end of the day, you have the result, but you really have no sense as to why it's true. I've just done a lot of calculation, and when the dust settles, the result is true, but it just seems like it's a miracle. I want to try to give you a sense of why it's true and that nothing else could conceivably have been true. So for instance, we're going to imagine other worlds and try to imagine what else could the Pythagorean theorem have been. And we'll see that the only thing that makes sense is a squared plus b squared equals c squared, modulo a few other things. But we'll see that other things initially could be proposed, but we'll see, no. It's not even worth trying to prove them. There's no way that relationship could be right. How many of you have seen dimensional analysis? You might have seen this in a chemistry class or a physics class. They sometimes call it unit analysis. Sometimes factor labeling, maybe, where you keep track of all the different units of quantities. It's often very useful to assign units to things and have things being of the same units. So let's look at our triangle. Let's imagine A, B, and C are in meters. Can anybody eliminate any of the proposed relations just by looking at units? So A, B, and C are in meters. What do you think? The cubes, right? C squared would be an area, and A cubed and B cubed would be a volume. So the first one is probably wrong. Can anybody eliminate another one? Another one of the proposed relations. The last one. Why the last one?
Because we know that even if it's just the coefficient, even if it's just 2, then it's the expansion of the term.
Good. Okay, so if it was a squared plus 2ab plus b squared, that'd be quantity a plus b squared. That would be a straight line. Right. So the coefficient is too large in the last one. It can't be more than 2. So what about the one above that, a squared plus ab plus b squared? Is that a possibility? So you're basically using the fact that if I give you a triangle, the sum of any two sides is greater than the third. And if I put the coefficient of 110, then I'm going to get that, the hypotenuse is larger than the sum of the other two sides. It just doesn't work. If I put in just an AB, this is a possibility. It's not too big. What about the second one, a squared plus 2b squared? Is there anything that's concerning about that? Yes. Either the second or the third. Give me something wrong or concerning about either the second or the third. Well, what could be dangerous if we subtracted? What could this give us for c squared? Well, give me some possible values of A and B and what that would give us for C.
Like if A is 1 and B is 2.
Mhm. Right, so one of the possibilities is C squared could become a negative number. So it's not just the C is a negative length. This would give us C as imaginary. What's a concern about the second one? Yeah, it's not symmetric. And so again, I'd be very suspicious about a relationship that is not symmetric in A and B. Right? Maybe B is the longest side. And I could see something like that, because if there is no longest side, then it would be symmetric when A and B are the same. But I would be suspicious about all of them. You know, the third one, I'm concerned because this can give us negative values. So the only one that really passes the test was the fourth one. Of course, it turns out that this is false. This is not the relationship in a right triangle, but it's a possibility. And it's not something that we could immediately eliminate. So I'm going to give you the dimensional analysis proof. This is my favorite proof of Pythagoras. So does everyone agree that area is a function of the hypotenuse C and the angle X? Once I give you the hypotenuse and the angle, then A and B are specified. And once A and B are specified, then I know the area. And if we know trigonometry, we could say A is equal to C times the sine of X, B is equal to C times the cosine of X, and then the area would be 1/2 C squared sine X cosine X. Now, we're not going to go that route. So the area is a function of the hypotenuse and the angle. I actually just told you how it depends on them, but let's pretend we don't know that. Does everyone agree that the area should be a function of the hypotenuse squared? If I double C, what does that do to A? If I double C, what does that do to A? And what does that do to B? So it increases the area by a factor of 4. So if I rescale the hypotenuse by a factor of r, it rescales the two sides each by r, so it rescales the area by r squared. So the area has to be proportional to the hypotenuse squared. The relationship with the angle is more involved, right? Just because we call something sine and cosine doesn't mean we really understand these functions. These functions are given by infinite series. They have names, so we talk about them, but they're still complicated functions to look at. So we agree that the area is going to be some function of the angle times C squared. And if you want, think of it as I'm just converting, if I rescale maybe from measuring things in meters to feet or yards to feet or something like that. I'm not changing physically the relative proportions. So I still have similar triangles. Okay, so now almost every geometry proof comes down to drawing an auxiliary line. And the question is, where is a good place to draw a line? We want right angles. So can anybody give me a thought about how we could draw an auxiliary line and generate some more right triangles or right angles? Yes.
Drawing two perpendicular lines from the center of C.
Okay, so one is I could go from the center of C down to B and over to A. That is one possibility. What else? Uh-huh. So I could go that way. What else? Two lines coming down from the hypotenuse. So perpendicular into C coming from where? Well, and what's the measure of the angle between A and B? So if you look at this triangle, what's the measure of the angle between A and B? I'm sorry? Yeah, it's 90 degrees. So that's actually the right one to do. So again, all of these were possible things to try. It turns out that this is the best one to do. And I'm going to give the triangles these wonderful names, triangle 1 and triangle 2. So we're doing a dimensional analysis proof of Pythagoras right now. What's nice is triangle 1 and 2 are similar to the original triangle. It's really easy to see this for triangle 2 because triangle 2 has a right angle. One of the angles is x, so the other angle has to be 90 minus x. It has to be similar. Similarly, for the other triangle, triangle 1, it has one of its angles is 90 minus x, so the other angle has to be x as well. So all three triangles have an angle x. What is the hypotenuse of triangle 1? A. What's the hypotenuse of triangle 2? B. And what's the hypotenuse of the big triangle? C. We just showed that the area is equal to f of x times hypotenuse squared. So by doing that, we know f of x times a squared, the area of the small triangle 1, plus f of x b squared, the area of the small triangle 2, is equal to f of x times c squared. Trying to get rid of a piece of something on my. I would just leave the damn thing on my. Oh, there we go. Okay. What should we do to both sides? We have f of x a squared plus f of x b squared equals f of x c squared. Cancel the f's. So does everybody understand how we got here? The area of the big triangle is just equal to the sum of the areas of the two small triangles that make it up. Yes. Well, that's what we said earlier, that if I give you a right triangle, we said that the area of a right triangle is proportional to the square of the hypotenuse. And so I don't know exactly how that depends on the angle. That's why we're calling it some function f of x. And what's important is that these triangles all have the same angle x. So it's the same proportionality constant for all of them. If they didn't have the same angle x, it'd be in trouble. Yes. Well, that's why I was trying to say that they were all similar to the original triangle. For triangle 2, notice it has an x over here. Yeah. For the other one, it has a 90 minus x. So if it has a 90 minus x and a right angle, then the other angle has to be x. How did you know that was 90 minus x? Well, because in the original triangle, if one angle is x, the other angle is 90 minus x. You're making them similar on purpose. Yes. Okay. Yes. When we come up and we draw the altitude from the right angle to the hypotenuse, we know that gives us another 90-degree angle. And then since the angle in the bottom right corner is x, then it has to split the right angle into x and 90 minus x. Yeah. So why can we cancel f of x from both sides? It's not 0. So you have to prove that. This is a math class, not an economics class or a physics class. We can't just cancel f of x.
We just say
yes.
The area cannot be 0.
Right. The area is not 0. If f of x equals 0, then it would be telling us the area is 0. And if I put two right triangles together, that's saying the area of the rectangle is 0. That can only happen if x or y is. So I'm not saying it's difficult to justify, but it has to be justified. You have to show that we do not have 0 area. And so when we cancel that, we get a squared plus b squared is c squared. And so this is a dimensional analysis proof of Pythagoras. You might have seen dimensional analysis in some other places. This is another nice one in physics. So how many of you have ever done the pendulum bob? Okay. Oh, are you? Oh, excellent. So good timing since you're doing this right now. Even better. Who's teaching it? Excellent. So in case you haven't done any physics, here's the configuration. We have a rigid rod of length L measured in meters. The acceleration due to gravity, g, is measured in meters per second squared. It's around 9.8 meters per second squared near the surface of the Earth. It does change a little bit, but given how big the radius of the Earth is, not a big deal. The mass is measured in kilograms. The period is measured in seconds. It's how long it takes to do a full cycle. And then the angle of the initial release will measure in radians. And radians is a unitless quantity. And so we want to try to figure out what is the period as a function of all these quantities. So we somehow have to get seconds. Can anybody tell me which objects might be involved in getting seconds and which objects might not be involved in getting seconds. So acceleration is the only quantity in play that has a seconds in it. So acceleration should be involved. Acceleration gives us a meters per second squared. How can I get rid of the meters? Yeah, if I divide by the length, or if I divide length by g, I'll get seconds squared. So how can I get from seconds squared to seconds? Square root. So it feels like there should be something proportional to the square root of L over G. Is the mass going to come into play? That gives me a unit of kilograms. Is there anything that can cancel the kilograms? No. So I don't expect that to come into play. So the only combination of the quantities that will get me seconds is some function of that angular release times the square root of L over G. So before we even go to the lab, if I were to double the length, well, let's quadruple the length. Let's be nice to myself. If I were to quadruple the length, I would expect the period to double. And so you have a rough sense, before you do any experiment, what kind of relationship should you get? The period should be proportional to the square root of L over G. It turns out that f of x is a constant. There's no way you're going to get that from a dimensional analysis like this. But it's amazing that you can just look at the pendulum and get a feel that it's going to be the square root of L over G times a constant just by looking at units. All right, so what I want to do now is I want to go to guessing Pythagoras. So we've proven Pythagoras, we know what Pythagoras is, we know how to prove it. Could we have guessed Pythagoras? And so one of the things we've already talked a little bit about this semester is putting in some free parameters. When we were doing the arithmetic mean, geometric mean, and we were trying to figure out when we were doing the downward induction, we wanted to not just say it's equal to a fixed sum, but maybe beta times the sum. And then the other one, which you were supposed to do at home, was not a fixed product, but a fixed product maybe to the delta power, to give me some parameter that I can then vary and hopefully make things work out. So I want to try to guess relationships between A, B, and C. And then I'll give myself some free parameters and see if there's any choice. So the natural guess is maybe there's a linear relationship. If the linear relationship doesn't work, try a quadratic. If the quadratic doesn't work, what should I try next? Cubic. I don't think it's going to be a mixed quadratic and linear because then I'll have things of the wrong dimension. So the simplest linear relationship I can think of is C is equal to alpha times A plus beta times B. So let's see if it's possible that there could be a linear relationship. What's the answer? Is there a linear relationship between A, B, and C? No, right? We know the Pythagorean theorem, so we know that this is doomed to fail. But let's try to see. Can anybody give me any information about if there is such a relationship, what would be true about alpha and beta, the subjunctive tense? Yes.
The combination has to be less than 2.
Good, the combination has to be less than 2. Why does the combination have to be less than 2?
Because if we're like 1 and 1, then C would be, let's see, the sum.
Okay, good. So if they're 1, 1, we know there's a problem. But maybe A is smaller than B. And so maybe we have a larger combination of the smaller one. So you're on the right track. What must be true about alpha and beta? What should be true about this relationship? So we've talked about this earlier. If I flip A and B, what should be true? It should be the same. So what should be true about alpha and beta? They should be equal to each other. So now your statement that their sum should be at most 2 becomes alpha equals beta and their sum, and each one is at most 1. In fact, each one would be strictly less than 1. Because if they were 1, then it would be too large. And clearly they can't be negative. Can anybody think of a good triangle to look at? An extreme case.
1, 1, 2.
Okay, but do you know about a 1, 1, 2 right triangle?
I thought you meant the next few cases was like a line.
So we may not know what A, B, and C are, but we might know approximately. So if I take some extreme values for A and B, can you give me approximately what C is? Okay, what would work? Good. Good. So take the extreme case where one of them is close to 0 and the other one is huge. And so we can take a long, thin right triangle, right? And so if I take a triangle like that, as A goes to 0, then C and B are almost the same, right? So what's the only possibility for beta? Beta has to be 1. Because in the limit as A goes to 0, C goes to B. Similarly, alpha has to equal 1. So does everyone agree that by looking at the limits of extreme triangles, we see that the only possibility is alpha equals beta equals 1? Okay, so now, does that make sense? Well, if C equals A plus B, this is the straight line, right? So that doesn't really make sense. But we can see it another way. As we talked about, the area of a rectangle, we know that is just length times width. The area of a right triangle is just 1/2 xy. Can you think of a nice triangle that we might be able to understand? There are 2 nice triangles that we have a chance of understanding. What would be a nice triangle? We don't know it's a 3, 4, 5 triangle. You have to use Pythagoras. So what are the natural right triangles or natural triangles that should be easy to understand? 45, 45, 90. So if we take a 45, 45, 90 triangle, if the relationship was C equals A plus B, then we would get the 2 sides would be 1, the hypotenuse would be 2, and the triangles fit together very nicely and give us the square. And so we can calculate the area of the square 2 different ways. It's 2 by 2, which gives us an area of 4, or what's the area of each right triangle? It's 1/2 length times width, which is just 1/2. And so if we do it that way, the 4 triangles is 1/2 4 times, which is 2. The area of a square of side length 2 is 4, contradiction. So by looking at the special case of the 45, 45, 90 triangle, we don't know initially what the hypotenuse is, but if we know that beta has to equal alpha has to equal 1, the only possibility would be the hypotenuse equals 2. This leads to a contradiction. So it can't be a linear relationship. So now we can try to do a quadratic relationship. And so we could say, alpha A squared plus gamma AB plus beta B squared. And we now want to figure out alpha, beta, and gamma. So what information can you tell me about alpha, beta, gamma? I know you know the values. I know because you know Pythagoras. But what can you tell me about the candidates? What can you tell me could be true?
Start with before, like what's symmetrical to a alpha to equal beta.
Good. So we know alpha has to be beta. Good. And do you know what that value has to be? So alpha has to be beta just as before, because it should be symmetric. What else should be true?
It should be equal to 1.
Yeah, they should be equal. Same thing as before. Consider the long, thin triangles. So if you take the limit as B goes to 0, A goes to 0, then C squared goes to A squared, or C squared goes to B squared. So alpha and beta both have to be 1. All right, so that's not so bad. Now it's just A squared plus gamma AB plus B squared. The difficulty is gamma. Okay? We have to try to figure out what's the possibility for gamma. Now, from your arguments before, we know that gamma should be at most 2 in absolute value. Otherwise, if gamma in fact is as large as 2, then you get c squared is a squared plus 2ab plus b squared. That means it's going to be a straight line. So we know gamma should be maybe between -2 and 2. All right, so let's again look at the 45, 45, 90 right triangle. And so now we don't know what the hypotenuse C is, but we know it's supposed to be a squared plus gamma ab plus b squared. So let's try to see what would make sense. So if we equate areas, and again, this is a key proof technique, calculate something 2 different ways. We have 4 triangles. Each triangle has area 1/2. There's 4 of them, so that gives us 2. So c squared has to be 2. So c has to equal the square root of 2. If c equals the square root of 2, we get 2 equals 1 plus gamma times 1 squared plus 1. So gamma has to be 0. So c squared is a squared plus b squared. Did we just prove the Pythagorean theorem?
How do we know gamma's always zero? I guess it's always.
Who proved it for this triangle?
We proved it for this triangle. We did not prove the Pythagorean theorem. We proved for this triangle. Yes. Right. Yes. So c squared equals 2. Each right triangle has area 1/2 base times height. Each right triangle has area 1/2. We have 4 of them, so the area of the square has to be 4 times 1/2 or 2. But you can also view this as a square that's c by c. And so if you view it as a square that's c by c, its area is c squared. So we're calculating something 2 different ways. Sure. There's 2 ways to calculate the area of this figure. One is it's a square that's c by c, so its area is c squared. The other is it's 4 right triangles, and each right triangle has area 1/2. So 4 times 1/2 is 2. So c squared has to equal 2. Yep. So we've just shown that if there's a quadratic relationship, the only quadratic relationship that works is when gamma equals 0. This does not prove that it always works. It just proves that in this case, you are going to have a quadratic relationship. Okay, so we've done this before about the differences between a proof and just checking special cases, right? I think I gave this on like the first day of class or something like that, right? And we saw that if you just cancel by dividing, it seems to work. But we do not believe that 12 over 24 is 1/4. So just because something works for a while does not mean it's going to continue to work. I'm not going to go into too much detail on the next one. If you want, you can look online for the slides. But it's natural to ask, well, what would happen if we went to a sphere? Is there a Pythagorean theorem on a sphere? How much spherical geometry do people know? I'm going to guess not much. In the plane, what is the sum of the angles of a triangle? 180. It could be larger on a sphere. Is it possible to have an equilateral right triangle on a sphere? Yes. Come down from the North Pole to the equator. Go from the equator a quarter of the way around, that's a right angle, and then go back up to the North Pole. You can actually have an equilateral triangle on the sphere where all the angles are 90 degrees. Now, if you have a sphere with a really large radius and you look in a small segment of the sphere, what does the sphere look like? It looks like a surface, it looks like a plane. And this is why for a long period of time, people did not notice things like the curvature of the earth and the effects of that. So imagine we have some kind of triangle like this with vertices A, B, and C, and the typical notation is to have the side opposite the vertex have a lowercase letter to denote the length. Is there a relationship between little a, little b, little c, and the angles big A, big B, big C? Is there a version of the Pythagorean theorem if we have a spherical right triangle? How many of you have ever seen this before? This is a natural question that you should have asked once you've seen Pythagoras. What else can I do with this? Well, we can write things down in spherical coordinates. I'm not going to go through the calculations in great detail. I am going to use the physics notation where theta is the angle coming down from the z-axis. And phi is the angle in the xy plane. Again, right now for this, you should not be paying too much attention to the details. Just know that there are details that can be done. Okay, we can write things down. Mathematicians and physicists have slightly different notation as to how they want to do things. I learned spherical coordinates first from the physicists, so I default to the physics notation. So what would the Pythagorean formula be on a sphere? Well, if A, B, and C are very small relative to the radius r, then we're essentially on a plane, and spherical Pythagoras should reduce to normal Pythagoras. And so from a dimensional analysis point of view, it seems natural that my answer should only depend on the ratios of A, B, and C divided by the big radius r. Because if I just rescale A, B, C, and r by the same amount, I don't change any relative proportions. So I want a formula that depends only on these ratios, and in the limit as big R goes to infinity with A, B, and C fixed, it's got to reduce to Pythagoras. And so this suggests that maybe a relationship involving cosines or sines of these ratios might come into play. And so again, I'm not going to go through all the details. Hopefully you've seen the Taylor series expansion of cosine. So if I look at the cosine of A over R, to second order, it's 1 minus 1/2 A squared over R squared. And then there's higher order terms and whatnot. And it turns out that with a little bit of algebra, the cosine of C over R is approximately the cosine of A over R times the cosine of B over R. Just when you put in everything together, you're going to get 1 for the main term for everything. Then you're going to get a negative 1 over 2R squared times C squared equals negative 1 over 2R squared times A squared plus B squared as the first order correction term on both sides. And then the next terms are going to be much, much smaller, of size 1 over R to the 4. This is not a proof, but it's suggesting that this might be spherical Pythagoras. It does reduce to the right answer as R goes to infinity for fixed A, B, and C. It does reduce to the standard Pythagoras. All right. What you could do if you wanted to do this rigorously is write down the coordinates for the points, calculate the lengths of the arcs, use dot product relationships. The dot product gives you a wonderful formula for the cosine of the angle in terms of the dot product. If you choose your coordinate systems nice to put in as many zeros as you can for the entries, you're going to simplify your life in dot products. So always do that. This is why we typically have maybe something is on the North Pole, just trying to make things a little bit easier. And when you go through and you do all the algebra, you do get spherical Pythagoras. So now that we have Pythagoras, we now have spherical Pythagoras using the standard trig functions. Can anybody suggest what might come next? What's another shape we could look at that involves generalizations of sines and cosines? You could do cylindrical, but cylindrical is really not quite right. Any other generalizations of sines and cosines that you know about? Not an ellipse, something related to an ellipse, though. It's another generalization of sines and cosines that sadly does not seem to be taught too much anymore. Hyperbolas, hyperbolic trig functions, right? And so there's hyperbolic spaces that you can look at, and there's a hyperbolic version of Pythagoras using the hyperbolic trig functions, the cosh. And so if you haven't seen these before, because I have seen in the past, students have not seen e to the ix. E to the ix is cosine x plus I sine x, or conversely, cosine x is 1/2 e to the ix plus e to the minus ix. How many of you have not seen this before? Okay, it's not always taught, which is a shame, that there is a relationship between the standard trig functions and the exponential functions. This is where all the trig identities come from. All the trig identities come from this exponential relationship. And maybe we'll talk a little bit more about that later in the semester. All right, so conclusion, and then we'll switch to something else. There's a lot of generalizations you can do. When you look at a book, it seems like everything's already been done. There's a lot that's out there. When you see math, always ask what's next. Try to extend to a higher dimension. Try to look at a different space. There's more than one way to prove things. And depending on which way you choose, you will be able to see different aspects of the problem. And sometimes one version generalizes better than another. Years ago, I had some summer students that were looking at a problem of trying to generalize something to higher dimensions. And they took the best paper in one dimension and tried to extend the arguments, and it did not work at all. And one of the reasons they were using that paper is that the previous summers group had written that paper. We were very proud of it. I said, this paper may be the wrong way to start. Let's go back to the very first paper in the subject, which has a much more elementary approach that might generalize better. And in fact, that's what worked. And so it's sometimes not clear what's the best way to go. So I will hopefully be able to toggle, yes. All right. So what I want to do is I want to end with a GRE problem. Can people see this one? Make it a little bit larger. I want to integrate from 0 to infinity the exponential of ax minus the exponential of bx over 1 plus exponential ax times 1 plus exponential of bx from 0 to infinity. A and b will be, let's say, positive numbers. Anybody feel comfortable about their integration prowess to get this in closed form? And then evaluate this at infinity and subtract it at 0. Then by all means, please, I look forward to your email. So my professor freshman year defined trivial as, and again, I don't think you could do this anymore. He could come into our dorm room at 2 a.m., wake us up, give us the problem. We could solve it immediately, go back to sleep, and sleep soundly. If you can do that, it's trivial. Otherwise, he wants a proof. Can you give me anything about A and B where you can evaluate this integral easily? Are there any choices of A and B where we know the answer?
A equals to B would be not that.
Good. So if A equals B, what do you get?
0 over
0. It's just 0. So because when A equals B, we get 0, we know that eliminates B. We know it has to be a function of A minus B, right? So must be a function of A minus B. All right, so we've at least eliminated one answer. What do you think happens as A gets very, very large relative to B? What do you think happens?
The right side terms don't matter. The b terms.
So definitely the minus exponential bx doesn't matter. But what about the b in the denominator? What can you tell me about the log of 2? It's a positive number, unfortunately. So I can't eliminate d as being a negative number. If I replace a with r times a and b with r times b, what does that do? If I replace x with, say, u over r, the r would cancel the r over there. And what does dx become? Becomes du over r. So there should be a really nice relationship. If I rescale a and b by r, then if I do this change of variable, it seems like I've decreased the integral by a factor of r. Which is the only answer that decreases by a factor of r? I'm sorry? Why C? So both C and D will be increased by a factor of R.
Oh, E because
E.
you have two terms in the
I have two, so if I do E, the denominator decreases by a factor of R squared. The numerator, so this is suggesting E. Right? Now we can also eliminate A, as it's not zero. Right? This integral is clearly not zero. Let A get very, very large. As long as A is greater than B, then we know that the integral is not zero because we're integrating something that's positive. So we can eliminate A without too much trouble. We can eliminate B without too much trouble. We can eliminate C and D by rescaling. And without doing any of this integration, just by doing some kind of like dimensional analysis, I know the answer is E. So as a challenge for extra credit, find the antiderivative of this function. And this is like a Mad Max world. There's been a terrible nuclear war. All electronics have failed you. You can only use pen and paper. All right? No computer-aided tools. Find the antiderivative of the integrand, if you can. Good luck. Okay, it may be doable. I don't know. I've never thought about it because the whole point for this problem is, can I eliminate 4 wrong answers? And the answer is yes. By just getting a feel for what goes on. That's what I want you to get out of this class. All right, stop the video.